In this video, we're going to say MOSFET in action, which means its working and its IV characteristics. So before we start, let's see quickly the three-dimensional model of MOSFET. Here is the three-dimensional view of the MOSFET. In very simple terms, these are source and drain terminals, and here we have oxide, and the black one that is colored is the gate, which is metal. And we have the substrate, p-type substrate, and a bulk terminal. We'll see the three-dimensional structure in even more detail when we go to IC technology, where we discuss CMOS fabrication. In this, if you look at the dimensions, this length from here to here is actually the drawn channel length. And this distance, that is from the source end to the drain end, this is actually the channel length, which means this is the length that an electron which starts from source in N-type MOSFET has to traverse and go to drain. This is called the channel length. This is the width, W. So when we operate this N-channel MOSFET in inversion mode, the electrons have to travel this distance, that is channel length, and the channel width is W. The higher the width, more scope for more electrons to actually flow. The higher the length, longer the distance the electrons have to flow. And if you observe that there will be a small overlap between the gate and drain, and in fact even gate and source. This comes as a effect due to how the MOSFET is manufactured. Now obviously we cannot be drawing the structure every time, so hence I'll take the two-dimensional model in a simpler form. That will look like this. So this is the 3D model and this is the 2D model. Now in general, when we look at the operation of N-channel MOSFET, we always connect the source and the body terminal together and ground it. Now in fact, the 4-terminal device, if you look at, it has become a 3-terminal device in a way, because 2 of the terminals are shorted. And because we ground the source, of course, whenever I say source now, it is same as bulk. So when I ground the source, now we have only 2 terminals to talk about, where we can control the potential. So the gate and the drain. In fact, we're going to talk about the potentials as VGS, that is gate to source potential, and the drain to source potential. The drain potential with respect to source. So we'll have 2 voltages to talk about. And of course, because this is oxide, there won't be any gate current flowing ideally. So we will never have to consider the IG. In fact, we'll consider only the ID. This is the drain current, which flows from drain to source. In fact, which means the electrons actually flow from source to drain, of course, when the channel is present. So this direction of current we are taking as reference going into the drain, which is ID. Now let's start and understand how the MOSFET works. So to start with, I'm taking the first case where both VGS is equal to 0 and VDS is equal to 0. In which case, as VGS is 0, there won't be any channel formation here, or even there won't be any depletion under the oxide in the silicon. Hence, the P substrate below the oxide would be exactly intact as it is in the bulk. But if you look at the source to bulk, there is a N plus P diode, in which case even under a applied 0 potential difference across them, there would be a depletion width under equilibrium. So I'm going to show the depletion width, and the same thing on the drain side as well, because this is again a PN junction diode. P is the substrate and N is the drain region, and there would be depletion width in the equilibrium. And the reason why I'm not showing the depletion region inside N plus is N is highly doped, hence it is called N plus. The depletion width inside the N will be very small compared to the depletion width on the P side here. This is how the MOSFET looks when the condition is VGS equal to 0 and VDS equals to 0. Now let's look at the second condition where VGS is greater than VTH. And let's say this is VGS is equal to VGS1, just for our reference, so that we can discuss other VGS voltages with respect to this. And VDS is equal to 0. Now let's look at the structure. I've represented the structure here. When VDS equal to 0, the drain is grounded, and VGS, the gate, has a positive potential which is greater than VTH, the threshold voltage. When gate is applied potential greater than VTH, we know that there would be inversion region formed below the oxide in the semiconductor, where the bulk at the interface is actually inverted. So let me draw the inversion channel. In fact, I am exaggerating the channel here so that we can discuss the operation of MOSFET in very simple terms. I have to draw the depletion widths on the source and drain side. That would still be with the same kind of depletion width even on the drain side, because drain is grounded and even the source is grounded. But of course, we know when there is inversion charge formed, there will be depletion width of XD max, as we have seen in the MOS capacitor, which means there will be depletion region below this inversion region. So let me show it here, that there is a depletion region under this. This is the inversion charge. Now we have a N plus region with a N plus channel and N plus drain. There is conductive path between drain and source. First two situations that we have seen here are conditions where there is no current actually flowing. We have just shown what will happen if VGS is 0 and VGS is greater than threshold voltage. How does the channel or the semiconductor under the oxide look like? So now we're going to switch gears and try to understand what will happen when VDS is changed, keeping VGS fixed. So I'm going to take VGS1 as reference. So in the entire operation that we discuss next, we're going to keep VGS fixed and then change VDS and see what happens to the current that flows through the channel. Now I'm taking VGS is equal to VGS1 and VDS is not equal to 0, and of course I'm assuming VDS is positive and it is small. In this case, let me draw the structure of the MOSFET. This is how it looks, and in fact, as we assumed, VDS is very small and positive. Obviously, when there is a positive potential here, there should be current flowing from drain to source through the channel, and electrons would be flowing from source to drain. When I say small, this would be few millivolts, let's say 25 millivolts kind of. In this situation, we can take this channel that is available like a thin sheet of conductor like this, through which current is flowing. We can say when we have a thin sheet of conductive material, let's say thickness, width, and then the length, it will be like a resistor, rho times L by A. So if you look at this, when VDS is small, the channel would offer some resistance and it would be like a resistor. Hence, as we slowly increase the potential at drain, which means as VDS is increasing, we would get linear increase in current because it looks like a resistor. This is ID, the drain current, and this is the drain to source voltage. Now let's see in the next case where we increase VDS beyond the small potential and see what happens to the channel and the current flow. If you take this case where VGS is still fixed and it is VGS1 and VDS is positive, but this time it is not small, the structure of the MOSFET would look like this. Now, how did I get to this point? So in order to understand that, I'm going to pull up the previous one and let's do a comparison. Right, if we look at this, here the VDS was very small. Hence, we didn't consider the potential drop across the channel. We assumed it is like a resistor and it offers some finite resistance. And hence, the current increases linearly for very small values of drain to source voltages. Now, we are increasing the drain voltage further where we cannot say it is any more small. In that case, we cannot neglect the potential drop across the channel. When we increase the potential at the drain, the current that is flowing through this channel should increase. Of course, whatever potential we are applying at drain, that potential should be here. And why would I say that is because the potential drop across this N plus region can be neglected because it will be highly conductive as it is N plus, highly doped. And at source, the potential is 0. Hence, the potential at this channel starting point can be assumed to be 0. If potential at source is 0 and potential at this point is VDS, which means the current that is flowing through the channel is dropping the potential along the channel. In that case, the potential is 0 here, the potential is VDS here, or VD. The potential is increasing from source to drain. So let me write that point here. Potential is increasing from source to drain. As the potential is increasing from source to drain, if you observe here that this is N and this is depletion region and this is P. If the potential on the N side is increasing with respect to P, which is in fact grounded along with the source, then this P-N junction is actually getting reverse biased. When it is reverse biased, the depletion region should increase as we go from source to drain. Hence, I've drawn this figure in such a way that the depletion region width is increasing as we go from source to drain. So let me write that down here. Depletion width or charge increases from source to drain. Now let's go back. As the depletion charge increases, obviously gate potential has not changed, which means the charge that comes on the gate has not changed. When we have a charge on gate, the underlying charge should be exactly equal but opposite, because after all it's a capacitor. Now, if that is the case, if depletion region charge is increasing, taking the charge here, let's say at a given point, if the charge is fixed on gate, if the depletion charge is increasing, then the inversion charge should decrease, right? So if I keep metal charge is equal to the depletion charge plus the inversion charge. Now this is fixed because I'm not changing the gate potential, but the depletion charge is basically increasing. This is constant, increasing. Hence, the inversion charge should decrease. As a result, as we go from source to drain, the inversion charge should reduce. So let me make that point here. Inversion charge decreases from source to drain. So that is how I have drawn this structure for this particular scenario. Now the channel thickness has reduced. As a result, the current that is flowing through would see a higher resistance now. The resistance of the channel would increase. But of course, the potential is also increasing. That's what we have discussed. But what will happen to the current? Obviously, current will be increasing, but the current that is flowing will be that VDS over the resistance that is seen. Both are increasing, and in fact, IDS increases, but it will not increase at the rate at which it was increasing before, because the resistance is not constant. Hence, if we draw the characteristics, this was for the first case that we have discussed, where it was linear. Now we are entering into a region which is not linear anymore. The rate at which the current was increasing wouldn't increase at the same rate as we had in linear region. It would be less now. The rate at which it increases would be less now. Now the interesting question is, if the channel charge keeps decreasing at the drain end, how much potential we have to apply at the drain where the channel charge would become, let's say, close to 0, or let's say 0. Let's investigate that point. So if we observe here, when VGS was greater than VTH, so when VGS was greater than VTH, what is the voltage that was actually creating the channel here? If you remember, when VGS is equal to VTH or below, there was no channel formation. When VGS is above VTH, which means VGS minus VTH is actually the potential that was actually creating the channel there. The excess voltage beyond the threshold voltage. We call this overdrive voltage. Overdrive. So you're driving the potential beyond the threshold voltage by how much? So that much potential is actually creating the channel. When VDS becomes this voltage, and of course on the channel when you apply this much potential from drain, it would be acting in the reverse way compared to gate, which means it would reduce the channel charge at the drain to a point where it almost becomes 0. So assuming when the drain potential is equal to VGS minus VTH, in this case this is VGS1 in fact, VGS1 minus VTH, let's see how the structure looks and what would happen to the current. This is how it looks for the condition where VDS is equal to VGS1 minus VTH. As we discussed here, that when VDS is equal to VGS1 minus VTH, the channel should become 0. But let's investigate, will it actually become 0 or not? Now from the previous discussion, let me just draw the IV characteristics here till what we have discussed. That is for VDS and ID. So we have seen 2 points. One was in the linear region and the other one where the resistance was in fact increasing. And now we are seeing this point at which the channel almost becomes 0. Let's see if it becomes 0 or not. To understand will it actually become 0, let's assume, let's say the channel becomes 0. If channel becomes 0, there should not be any channel for current to flow through. But of course, what actually made this channel to reduce was actually the current itself. The reason for the channel to reduce was the current. If current is not going to be there, then the channel would never close, which means the channel would never close. So hence we can say that the channel would never become 0. But then what will happen? Think about taking a pinch of salt between your fingers. So when you take a pinch of salt and actually shake it off and ask someone, what am I holding between the fingers? People would say, I will probably nothing. But if you see, the fingers wouldn't be touching each other because there is a fine layer of salt. That's called a pinch of salt, isn't it? So now, in this case, the channel would be to a point where the channel is pinched off, so that you would feel as if the channel is 0, but the channel is not 0. It has to exist because the reason why the channel is reducing is because of the current itself. It cannot stop the flow of current as such. Hence what happens is the channel would become 0 almost, but I would say it is pinched off, and hence the current would reach to its maximum value, beyond which the channel would not allow current to increase even if you increase VD. So let me draw that here. Now the third condition that we are seeing is we hit a maximum point here. Let's say this is for VDS is equal to VGS1 minus VTH, this point at which current reaches to maximum value, and beyond which if you increase the drain potential, the channel is not going to allow the current to increase because that's a maximum that it will allow. So hence beyond which the current is going to be constant. So this is how the characteristics of ID versus VDS will look. We have discussed the first case earlier, this is the second case, and now this is the third case. Of course, barring the first two figures that we have seen, let me just show you the figures. So the first one was this, where we had linear region, and then we went into a region where the resistance increases and current, the rate at which the current increases with respect to voltage is not going to be similar in this case compared to linear region. And then when we come to the third one, the current would become max value and the channel is not going to allow the current to increase anymore. Hence, even if you keep increasing VDS, the current is not going to increase. This current is called the saturation current, beyond which it cannot increase. And by the way, this figure is for VGS is equal to VGS1. But now let's understand what will happen if we increase VGS beyond VGS1. So when we increase VGS greater than VGS1, you have extra overdrive voltage, which is VGS. Let me call that voltage as VGS2. So the second case is VGS is equal to VGS2. VGS2 is greater than VGS1. In that case, VGS minus VTH in this case is higher than this case, which means the channel formation would be higher in this case. So to start with, the resistance would be less because the thickness would be higher, or even the concentration of electrons in the channel would be higher. As a result, when resistance is less, the current increase with respect to potential would be higher, and it enters into slightly nonlinear region. And then by the time we hit VGS2 minus VTH, when VDS becomes VGS2 minus VTH, we'll hit a saturation point, and then the current would become constant. So this will be the point for VGS. This is VGS2 minus VTH. Now let's take another case where VGS is equal to VGS3, where VGS3 is less than VGS1. In this case, the overdrive voltage VGS minus VTH in this case is lower than this one. Hence, the channel to start with would be smaller. Hence, the initial resistance that you would see would be higher. Hence, the current increase with respect to potential would be smaller. Hence, we get current characteristics like this. And in fact, we hit the saturation point early because in this case, VGS3 minus VTH would be smaller. When VDS becomes VGS3 minus VTH, we hit the pinch off point of the channel. Hence, the current would be constant afterwards. So now if we connect all these dots of when the channel actually pinches off, we call this region as saturation region and this region as linear region. And to be precise, only for very small values of VDS it is linear. This is not linear in fact, but in general, just to differentiate the saturation region, we are calling this entire region as linear region. We can say that if VDS is less than VGS minus VTH, we can say this is in linear region. And if VDS is greater than VGS minus VTH, we can say this is in saturation. In fact, we can actually get this current equation for the MOSFET, that is ID is equal to mu, that is the mobility of electrons, as this is n channel, mu C ox prime, that is the capacitance per unit area, W by L. Of course, we have seen if the width is more, which means the width of the bridge is more number of cars can go. So if the width is more number of electrons can go. That's why the current would be higher if width is increased. But when you see the length, when length is increased, the more the distance the electrons have to travel. And of course, if the length is increased, the resistance would increase. Hence, when L increases, current would decrease. Mu C ox prime W by L times VGS minus VTH times VDS minus VDS square over 2. And if you plot this equation, irrespective of condition, what will happen is it will follow this curve and it would actually drop off like this. But this part is not part of the characteristics, by the way. Please note, this is only to show what is this equation. But if you look at this equation, if we substitute VDS is equal to VGS minus VTH, that is this point, beyond which the current is going to be constant, isn't it? Hence, I'm going to substitute VDS is equal to VGS minus VTH. Then I can get what is the current in saturation region, right? In all cases, I just have to put VGS minus VTH as VDS. So when we substitute, this becomes VGS minus VTH whole square minus VGS minus VTH whole square by 2. So we can write this as mu C ox prime W by L times VGS minus VTH whole square over 2. But of course, this is the current that is in saturation region. So I'm going to put this. This equation is valid in linear region where VDS is less than or equal to VGS minus VTH. And this is valid when VDS is greater than or equal to VGS minus VTH. And we have seen that at VDS is equal to VGS minus VTH, both equations are correct. That is how we actually found this equation from this equation. And of course, in this video, we are not going to derive how did we get this equation. But if it is required, we'll make it in a different video. In fact, so far we have seen only characteristics of ID versus VDS. Now let's see what is ID versus VGS. And in fact, that is simple to find out. So I'm taking it here. Let's say if you are in saturation region where I'm going to fix VDS, because if you remember, the way we understood ID versus VDS is when we fix VGS. Hence now, to understand ID versus VGS, I'm going to take VDS fixed. But of course, you have to note, I'm taking it in saturation region now. In that case, ID versus VGS. Of course, till VGS is threshold voltage, there won't be any channel, right? Hence, there wouldn't be current. But beyond which, what happens is, as you see here, this is for VGS3, this is VGS1, VGS2. So as VGS is increasing, the current keeps increasing. But in what fashion? In saturation region, we have the current equation like this, which is VGS minus VTH whole square. This is like a parabolic curve. So I'm going to draw it here that the curve would look like this. Threshold voltage would be somewhere here. This is ID versus VGS characteristics in fact saturation region. But the common question is, when we enter into linear region, what would happen? So let's see, only for one particular VGS, let's say at a given VGS in saturation, if you move that point into linear region, the current would decrease. So if I fix VDS in some linear region compared to saturation region, for the same VGS, the current is going to decrease. I would get different curves like this. This will be in linear regions, okay? This will be in linear regions, but in saturation region, however you change the VDS, this curve is not going to change. But in linear region, the curve keeps changing because as we move VDS, the currents are going to change. So these are the characteristics of MOSFET. In fact, to be specific, it is N-channel enhancement mode MOSFET, ID versus VDS and ID versus VGS. And we have two most important equations, that is current equations for linear region and for saturation region. If you guys find this video helpful, please don't forget to press the like button. If you haven't subscribed to the channel, please do subscribe, and thank you for watching.